This conference will now be recorded.
Hello everyone. So in this video we will discuss previous year's questions from NEET exam, and that is from the chapters Basic Principles of Organic Chemistry. So here we have the first question: which among the following compounds or species is least basic? Now least basic mentioned, and you can see in all the four species there is presence of NH2 group. And when there is presence of NH2 group, there is also presence of lone pair. So basically we have to find in which case the lone pair availability that will be minimum, because when lone pair availability is minimum, that will lead to least basicity. Now in the first case here, this type of resonance is possible, and when resonance is occurring, now nitrogen will be positively charged and negative charge will be generated over oxygen. What about the second molecule? Here also this lone pair, it will try to stabilize the positive charge which is present over carbon. Okay, now carbon is becoming neutral, but NH2 is positive. Resonance is also possible in this case, that is number 3. In this case, again, nitrogen is positively charged, and here we will have, sorry, this double bond will not be present anymore. Now there will be negative charge over this nitrogen. Another NH2, there is no change. Same type of resonance is also possible in the last case. Now this nitrogen will become neutral. So basically you are getting another equivalent structure. See, this structure and the structure given in 4, both are actually same. But we have to find in which case the least basicity we can expect. So in all the cases, this type of resonance is present, right? Now first of all, if you look at these 4 species, here compound 1 and this one, that is option 1 and option 3, in these 2 cases, there is no positive charge present. Just forget about resonance for some time. Just consider whether the molecule, overall molecule is neutral or not. Now the molecule in 1 and 3, these 2 are basically neutral. There is no positive charge. That means lone pair availability comparatively it will be high than the species present in option 2 and 4, obviously, because there is some positive charge. So 1 and 3 we will not choose. Now among 2 and 4, here we have positive charge which is close to NH2 group, right? And that is the reason that here you still have 2 free NH2, but here you have only 1 free NH2, and also the positive charge that is closer to nitrogen. And in this case, this positive charge comparatively it is not so closer to nitrogen. So if we apply this logic, then option 2, in this case the lone pair availability that will be even lesser, that is compared to 4. And in 4 there is 2 NH2 groups, so still you can say that the lone pair will be available on 2 different NH2. So considering all this, least basicity will be expecting from this option 2 species. Fine. Which among the following compounds will show geometrical isomerism? Now to show geometrical isomerism, first we will draw all the structures, because here only the names are given for the compounds. The first compound, pent 1-ene. So parent chain there will be total 5 carbon, and in one position there will be double bond. Now come to the second one, 2,3-dimethyl but2-ene. But means total 4 carbon. 2 position and 3 position there is 2 methyl groups present, and at 2 position there is also double bond. Now come to the third molecule. It is prop, that means total 3 carbon. And at 1 position we have double bond. 2 position we have methyl group. And what about the last one? In case of last one, it is hex. So first we will draw all the 6 carbon in the parent chain. So this is 1, 2, 3, 4, 5, 6. At 3 position you have to place methyl group. At 4 position also there is methyl group. And at 3 position there is double bond. Now we will check all the molecules whether geometrical isomerism possible or not. Here in the first molecule, 2 hydrogens are present, when similar groups are present on this carbon which is part of the double bond. So these 2 carbons are part of the double bond. Here you have 2 similar groups, so no question of choosing which one is higher priority. So how we can get GI? So GI is not possible. GI means geometrical isomerism. Now the next one also, we have similar groups, 2 methyl group across this CC double bond. Here also GI not possible, just like the previous one. Come to the third one. In third one also same problem. Similar groups present, so you will not be able to choose priority. Basically what we do, we choose priority on a particular carbon, and that is the 2 groups that is present, we choose priority. So same thing you can do for molecule 4. Here we have ethyl group and methyl group. So this is having more priority, and the other carbon of the CC double bond, methyl and ethyl. So this is more priority. Now 2 higher priority groups, they are on the opposite side. So that is why ultimately this will be able to show geometrical isomerism. And it's another geometrical isomerism that will be like this, where both the ethyl groups will be on the same side and methyl group on the same side. So this is the GI of the molecule which is present in 4. So that is why this will be the correct option, not the other 3. The correct order for the rate of alpha beta dehydrohalogenation for the following compounds. Alpha beta dehydrohalogenation, we have to understand the meaning of this line. Dehydrohalogenation, first focus on this term. Hydro means H and halogen means X. X may be F, Cl, Bri. Now D means you are removing these 2 species. So just like we say dehydration, dehydration means minus water. If I say dehalogenation, that means minus halogen, 2 halogen together. So when I am saying dehydrohalogenation, that means here H and X in the form of HX will be removed from the molecule. Now if you look at these 3 molecules that are given in the question, you have which halogen? You have iodine. So iodine will be removed along with some hydrogen. And these alpha and beta, these are the positions of these H and I. So that is why we are saying it alpha beta dehydrohalogenation. Now I can show this with some simple compound. So suppose you have this compound, iodine. Now this position is alpha with respect to iodine. This position is beta with respect to iodine. Now at beta position you have hydrogen. So when you have this type of presence of H and halogen at position alpha and beta, or you can say at position 1 and 2, because this is 1, this is 2 compared to, that is with respect to iodine. So now you can remove this H and I. So when you are removing this H and I, which happens in presence of some base, so this bond will be broken, this will be broken. So ultimately you will get CC double bond. So this will be the reaction that we are going to do for the molecule 1, 2 and 3. Now for molecule 1, 2 and 3, if we consider 1, here this position is alpha, this position is beta. That means the product that you will get after removal of HI, it is this one. Similarly, from molecule 2, this is alpha, this is beta. So if you remove H and I, you will get double bond at this position. Similarly, if you do the same thing for molecule 3, here this is alpha, this is beta. So we will remove these 2 atoms and we will get this species. So we are getting basically a new CC double bond in the product. Now the correct order of rate of this process, the rate of dehydrohalogenation. Now rate will be high when the species that you are getting after removal of HI, that species is very stable. Then only the process can occur very fast. So basically what you have to do, you have to find the stability order of these 3 products that you are getting from 1, 2 and 3. Now among these 3, these will be maximum stable. Why? Because you have 2 double bonds, and not just 2 double bonds. The position of these 2 double bonds are such, you can get this type of resonance. So the resonance structure, it will be, now negative charge is here, positive here. So because of this type of resonance, this is very stable. But that is not possible in case of 2 and 3 because you just have only 1 double bond. Now 1 will be at first, that is maximum rate is possible for this one, but that is present in option 3 and also option 4. 1 and 2 you can cancel, but how to choose between 3 and 4? Now you compare 2 and 3. In case of 3, this CC double bond, there is 2 methyl substituent and these 2 positions there is hydrogen. But if you consider the double bond in molecule 2, here you have only these methyl substituents. Now we know when number of this alkyl substitution is higher, more is the substitution in CC double bond, more will be the stability. But what is the reason behind it? The reason is number of alpha, that is hyperconjugable hydrogen or alpha hydrogen, that will increase. So in this methyl group, you have 3 hydrogens, and compared to CC double bond, this is alpha carbon. So these are the alpha hydrogens or hyperconjugable hydrogens. So you have total 6 hyperconjugable hydrogens. But see, in molecule 2, this is position alpha, where you have just 2 hydrogen, alpha hydrogen, that can take part in hyperconjugation with the CC double bond. So that means 3 should be more stable because of higher number of hyperconjugable structures, and that is why 1 will be at first position, because you can get resonance here, which is not possible in case of 2 and 3, and this factor will predominate. So you have to keep 1 at first position, after that 3, and then 2. So maximum rate of dehydrohalogenation, it will be for this molecule, then this one, then 2. Okay, option 4 is the correct option. Now this is comparatively easier. It is simply asking the number of sigma bonds, pi bonds, and the lone pair of electrons present in pyridine. So you have to know the structure of pyridine. So pyridine is just like benzene, only difference is one of the carbon, now there is nitrogen. Rest of the things just like benzene. And you know in benzene there is also hydrogen. So these are the hydrogens. And there will be lone pair only over nitrogen, because in case of carbon, when it is substituted like this, there is no question of lone pair, and also hydrogen there is no lone pair. Now if we consider the sigma bond, okay, pi bond is 3, only 3. This is pi, this is pi, this is pi. Now 3 pi bond that you can get in both option 1 and 2, but in option 2 only 1 lone pair. So lone pair is 1, pi is 3. Now 3 and 1 that you can get only in option 2. So even if you do not count sigma bond, because that will take much time. So if you are sure about the structure, if you know the pi bonds and lone pair, then that is enough to answer the question. But we will count here the sigma bond. So here sigma bond is obviously these carbon hydrogen bonds, total 5 carbon hydrogen bond. And here we have some CC bond and CN bonds. So these are the sigma bonds, 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5, 6. Total 6. That is 2 CN bonds and 4 CC bonds. But whatever it is, total number of sigma bonds, 11. So sigma bond 11. So 11, 3 and 1, that is matching with option 2. So that is why this is the correct option. Okay. Consider the following compounds or species. Here we have total starting from 1 up to 7. Total 7 structures you have. Now out of this you have to find the number of compound species which is obeying Huckel's rule. Obeying Huckel's rule means you have to check which are actually aromatic. Now the conditions for aromaticity is it must be cyclic. There must be full conjugation. So what I am trying to say by full conjugation means in the whole ring conjugation should be there. If it is partial conjugation, it will not satisfy the condition. It must be planar, and the most important, 4n plus 2 pi electrons must be present. Now all these 4 conditions when fulfilled, then only it will show aromaticity. Now come to the first one. The first molecule is naphthalene. Here we have total 1, 2, 3, 4, 5, total 5 pi electrons. So 5 pi electron means total 10 pi electrons will be there. Now if it is it satisfying 4n plus 2? Yes. When you put n value equal to 2, it is 4 into 2 plus 2. That means it is 10 pi electron. Now it is planar, it is cyclic, and throughout this whole 2 ring there is conjugation possible. So all the conditions are fulfilled. So that means this should be aromatic. What about the second molecule? The second molecule also 1 negative charge, 2 double bonds. So total, and this double bond can take part in resonance like this. So that means here 6 pi electron, Now when you put n value as 2, then 4n plus 2 becomes 6. So this is also aromatic because rest of the three conditions, planar, full ring conjugation, cyclic, everything is fulfilled. So this is also aromatic. Now the third one, sorry, it will be third. Here, this type of resonance is possible. It can, the double bonds can exchange their position, but total number of pi electrons, it is 4. Now, it is true that it is cyclic, full conjugation present, it is planar, but it is only 4n per electron, which is not matching with 4n plus 2. So, this is basically anti-aromatic. Okay? Because anti-aromatic, the rules are, all the first three you have, it should be fulfilled. But instead of 4n plus 2, now you will have only 4n. That is the difference between anti-aromatic and aromatic. Now, for 3, we will not count it, right? Come to number 4. Now 4 is just like 3 because in 4 also you have one negative charge, one double bond. So ultimately it is again 4 pi. Here also conjugation is possible. So this is also anti-aromatic just like 3. Come to the 5. In 5 you have 2 pi electron. Now when you put n equal to 0, 4n plus 2 becomes 2 pi electron. So that means here also conjugation possible. It is cyclic, it is planar. So this is also aromatic. Then number 6. Now number 6, there is total 4 pi electrons. That means total 8 pi electrons will be there. Again, it is matching with 4n, not 4n plus 2. So no question of aromaticity. And it is also not anti-aromatic because though it looks planar, but actually this molecule is not planar. So after all, as it cannot maintain planarity, ultimately it becomes non-aromatic. But we are just interested in aromatic compound. So whether it is anti-aromatic or non-aromatic, that is not the question here. Come to the last one. Here we have total 3 benzene ring. So it is naphthalene, but this molecule is called anthracene. So in this case, if you count 1, 2, 3, 4, 5, 6, 7, that means 7 into 2. In each bond there is 2 electrons, so total 4 pi electron. Now is it matching? Yes, it is matching. Why? Because now when you put n value as 3, 4n plus 2 becomes 4 into 3, 12 plus 2, 14. Now this is also planar cyclic, full conjugation is possible. That means this will also be counted as aromatic. So ultimately what we are getting? We are getting 1, 2, 5 and the last one which is 7. Okay, so 1, 2, 3, 4. 4 should be the correct option. Total 4 species. It is a integer, but integer that you have to find from options. So after all, it is MCQ type of question. Okay. Here we have two statements. Statement 1, statement 2. The statement 1 is saying that acidic strength of monosubstituted nitrophenol. Now when I am saying nitrophenol, phenol is this one. Now with respect to OH, the position of nitro, it can be at ortho, meta or para. Now the first statement is saying that acidic strength of monosubstituted nitrophenol. Which monosubstituted, ortho, meta, para, that is not mentioned. Simply mention monosubstituted nitrophenol. So acidic strength is higher than simple phenol because of electron withdrawing nitro group present. Now acidic strength means if you remove this hydrogen, what you get? You get phenoxide ion. Now this phenoxide ion, the negative charge will be stabilized if there is some NO2 group present at any position. Now it is true that if the NO2 groups are present at ortho position and para position, then NO2 group will be able to show minus R effect as well as minus I effect, both. But when NO2 group is present at meta position, then it will be able to show only minus I effect. But whatever it is, still it is some electron withdrawing effect. So when there is no NO2, it is simple phenol. And when there is NO2, irrespective of its position, it will always increase the acidity. So statement 1 must be true. Now come to statement 2. In statement 2, it is saying that orthonitrophenol, metanitrophenol, para. That means 3 different types of substitution will have same acidic strength as they have one nitro group attached to phenolic ring. So this is the logic. that it is saying that all of them will have same acidic strength, and then as the explanation it is giving because they are having only one. But see, depending on the position of NO2 group, the acidic strength will differ. So second statement you cannot say it is correct. First statement is only correct. So statement 1 is correct, but statement 2 is not correct. That is the question. But though it is not exactly required what is the order of acidity in case of different types of nitrophenol, but still we will discuss it, because if you get question related to acidity of different types of nitrophenol, then also you will be able to answer. So here the first three molecules, they are substituted, and see, this is simple phenol which is at the last position. So this is the acidity order. Now ortho and para, these two are ortho and para, that is having more acidity than the meta. This is meta, because at meta position it can show minus I effect, but minus R and minus I both possible in case of para and ortho. That is the reason that meta will have less acidity compared to ortho and para. So the next question is, why para is more acidic? Now the reason why para is more acidic, in case of ortho, this type of, see, I am writing the NO2 group in this way so that you can understand the hydrogen bonding that is actually present between this H and O minus. So this type of, see, six-membered ring type formation is there because of this hydrogen bonding. Now it becomes very stable. Now as a result, what is happening? This hydrogen is now not so free compared to the hydrogen in case of para-nitrophenol. So this hydrogen is involved in this type of hydrogen bonding, so its availability becomes less. That is why ortho substitution when present, that will be having less acidity. Okay, so these are the reason why we are getting this type of acidity order. But here correct answer will be this one. Statement 1 is correct, not statement 2. The incorrect statement regarding chirality. The first one is saying SN1 reaction yields 1:1 mixture of both enantiomer. So we'll try to see simply what SN1 is. So suppose I am starting with the tertiary butyl, that is Me3CCl. Now there is some nucleophile attacking, but before the nucleophile attack, first there will be generation of this type of carbocation, and that is the rate determining step or slow step. So here we are getting positive charge over carbon, and this carbon is attached to 3 more methyl groups, and then there is nucleophile attack. It is not directly attacking. Now now we are having some positive charge over carbon, which is basically our carbocation, and this carbocation is basically planar because it is sp2 hybridized. Now the nucleophile can attack from both sides. So as it can attack from both sides, now the initial chiral, sorry, here I should draw some chiral center. So let me, because when I am placing 3CH3, it cannot be chiral. So let me write it in this way. So suppose with carbon, there are 3 different R groups, R1, R2, R3, and then there is some leaving group. So first there will be formation of this type of carbocation, and this is basically planar. So nucleophile can attack from both sides. So initial configuration, suppose if it is R, and now the nucleophile can attack from both sides. So you will be getting some racemic mixture, and the chance of attacking from both sides equal. So that is why the formation of R and S, both these chances 1:1. So that is why this statement is basically correct. It is true, but we have to find incorrect. So that is not our correct option. The next one is saying that the product obtained by SN2 reaction of haloalkane having chirality at the reactive site shows inversion of configuration. Now this is also true, because in case of SN2 what happens? Suppose the similar type of structure if I am drawing, this is chiral center obviously, and in SN2 it is actually single step. So there is no intermediate formation like SN1. So it is single step, and in single step there is always inversion occurring. So remember, it is clearly mentioned chirality at the reactive center. So chirality must be present at that carbon which is carrying the leaving group. If chirality is present somewhere else, it doesn't matter. Okay, it must be present at the chiral center, and there is inversion. So this statement is also correct. Number 3, enantiomers are superimposable mirror images on each other. Now they are having some mirror image relationship, but it is not superimposable on each other. And just like our hands, if we take the see our two left hand and right hand, they are mirror image to each other. But when you try to place the right hand on the left hand, your thumb direction will be on the both sides. So just like that for molecules also, they are not superimposable. So this is actually the incorrect statement, and that is why option 3 will be correct. And the last statement, racemic mixture shows zero optical rotation. So it means, suppose you have some enantiomer, and racemic mixture means both R and S, it is present 1:1. So if R is rotating, suppose plus x degree, then S will be rotating minus x degree. And as they are present in same amount, sorry, so this will be cancelled by this, and after all, there will be zero optical rotation. Okay. So this statement is basically correct. Only the third one is incorrect. The Kejel's method for the estimation of nitrogen can be used to estimate the amount of nitrogen in which of the following compounds. We use this method for estimation of nitrogen in organic compounds. Suppose we have any organic compound where total number of carbon is X, total number of hydrogen is Y, and there is presence of some nitrogen. Suppose 1 nitrogen or 2 nitrogen. So how to know that nitrogen is present in the organic compound? We use this method. But you cannot apply this method for just any organic compound having nitrogen. There is some specific conditions that you have to follow. Now look at the options. Here you have different types of nitrogen present. Here nitrogen is it is heterocycle molecule, which is already part of the ring. Here we have NH2 group separate. Then here we have some azure group. Here we have nitro group. So we have to know the conditions. Now in Kejel's method, what happens? The nitrogen which is coming from the compound, when in this method we treat the molecule with sulfuric acid, and the nitrogen from compound, it forms this type of ammonium sulfate. Now this ammonium sulfate, in the next step we treat it with some sodium hydroxide. We get ammonia, and this ammonia is then treated with acid, and there are some extra steps for this, but details it is not required here. We just have to know in which case we cannot apply this method. So this method is not applicable to the compounds containing nitrogen having nitro and azure group and nitrogen present in the ring. So these are the three conditions: number 1, number 2, number 3. So number 1 you can get, that is nitro group in this one. Azure group is present here, so not possible. Nitrogen present in the ring, PDD. So this is also not possible. Number 3 conditions is present here. So only one option is left, which is aniline, this one. So why these compounds you cannot apply? This method you cannot apply because these compounds do not change to ammonium sulfate under these conditions. So this first reaction, if it is not occurring, then how you will be able to do the next steps? This must occur. Okay, so that is why aniline will be the correct option. What is the hybridization shown by C1 and C2 carbons respectively in the given compound? Now you have to recognize where from you will start the numbering, because C1 and C2 means what? You have to number the molecule properly. So let me draw the molecule first. We have CHO group at the left hand side. Then we have CH, double bond CH, CH2. Then we have COOCH3. So we have some A star. Now when you have A star, you have to start the numbering, not this carbon, but you have to start the numbering from here. So this is actually C1, this is actually C2. Now C1 is carbonyl group, so it is basically sp2, and this is sp3. It is not part of any double bond or triple bond. Sorry, sp3. So sp2 and sp3. That means option 1 is the correct option. So in this molecule, basically, rather than recognizing which carbon is sp2, sp3, because that is comparatively easy, you can do it easily. But here the question is tricky because first you have to numbering, that is, first you have to do the numbering, which is the main important part in this question. If you start the numbering from this side, it will be completely wrong. Because if you start from this side, you are putting, suppose you are thinking this is C1 and this is C2, then both will be sp2. Then you will incorrectly choose the option 2, which is not correct. So now when you have aldehyde group, you have ester group, you have to give priority to the ester, and that is why numbering is starting from right hand side. That is from the ester side. Okay. The compound which shows metamerism. Now, what is metamerism? Here in the options, we have some carbon, hydrogen, oxygen compound. Only in option C, we have hydrocarbon. But rest of the three containing carbon, hydrogen, and oxygen. Now, what is metamerism? It is a type of isomerism, obviously. So, it is observed when different alkyl groups present along both sides of polyvalent functional group. So, it is not just possible for monofunctional monovalent functional group. That means if you want to apply it for OH group, for NO2 group, for NH2 group, no, it is not possible. It is not polyvalent. Polyvalent group means suppose something like this, carbonyl, or it may be some 2-degree amine, or it may be ether, where both sides you will have some substituent. Because the definition of metamerism is different types of alkyl groups. Different alkyl groups means number of alkyl group may be different both sides. Suppose one side 1 carbon, another side 2 carbon. Sorry, 1 carbon and 3 carbon, and then take its metamer. There is 2 carbon, 2 carbon both sides. So that is one way metamerism can be observed. Or sometimes different alkyl groups means different types of branching may be present. So suppose one side there is no branching, another side there is some branching. So whatever it is, there must be some different alkyl groups. If it is present, then only this type of metamerism is possible. So it is observed in this type of functional groups, secondary amine, where both sides there will be some substitution. So that is, it is polyvalent. Now come to the first one, C3H6O. Here from the ratio it is clear, it will be either ketone, and the simplest ketone is this one. And it is also possible with aldehyde, but aldehyde group is not polyvalent. It is only from one side. Another side there is hydrogen is fixed. So this is also not possible. Only this type of groups you can apply metamerism. So C3H6O, it is basically nothing but ketone. So this will not show metamerism because you have you cannot change this. You cannot have both the methyl group, sorry, both the methyl on same side. Then it will not be keto group anymore, right? Now what about B? In case of B, we have 4 carbon, 10 hydrogen. Now this type of ratio, it is for ether. Now for ether, total 4 carbon. Suppose this is one structure where you have 1 carbon on one side, 3 carbon on the other side. But you can also have structure for this where 2 carbon both side. 2 carbon, 2 carbon. Here 1 and 3. So now it will be able to show metamerism. In case of C, it is basically hydrocarbon. Here no polyvalent functional groups are present. Polyvalent functional group not present. Okay, so that is why it will not be able to show metamerism. And the last one, C3H8O. Now again it will satisfy some ether, but you have only 3 carbon. Total number of hydrogen is fine. CH3, CH2, CH3. And everything is matching with this formula C3H8O. But here you have 1 carbon and 2 carbon. You cannot have one more variety. At least C4, at least 4 carbon must be present for the ether to show metamerism. Okay, so that is why this will also, though ether is present, but it will not show metamerism. Second option should be the correct option, right? Dihedral angle of least stable conformer of ethane. Ethane is C2H6. Okay. Now if I draw it so horse, it is I can also write it like this, CH3 CH3. Okay, now if I draw it as a horse, suppose this is the front carbon, this is the rear carbon. So front carbon we have 3 hydrogen, and the rear carbon, that is also 3 hydrogen. Now to understand this dihedral angle properly, better you consider the Newman. So here you can see the Newman. If I convert this Sawhorse to Newman, you will get this type of Newman, where all the hydrogens, you have this type of groups. So here these two are eclipsed. So this is eclipse conformation, and it is asking dihedral angle of least stable conformer. So you just have to know how many different types of conformations are possible. So what we will do, we will rotate this carbon. So when we are rotating this carbon gradually, this is basically least stable. Okay, dihedral angle in least stable conformer. And what is dihedral angle? It is the angle between these two. Okay, so see, when we have rotated it 60 degree, you are getting this configuration, and here the angle is now changed to 60 degree. Now this is actually more stable because this is staggered conformation. Now if you look at this graph, we have rear carbon rotation angle because we are just rotating the rear carbon, the back carbon. We are not disturbing the front carbon. So when you rotate the back carbon, when it is 60 degree, then energy is minimum. When it is 180 degree, then also it is minimum. So you are rotating, this is 60 degree, then at this position it will be 120 degree. So in this way it will change. Fine. So at 180 degree also you can also draw all the structures. You will see there will be minimum. But when it is 0, that means we are starting from this position, and when it is 0, that is the 0 dihedral angle, its energy is very high. It is also true for 120 degree. 120 degree structure will be like this. So 120 degree means front carbon we are not changing, but back carbon this is 60 degree, but one more 60 degree we are rotating, that means now it will be something like this. So see, here also it is another eclipse conformation you are getting, right? So that is why this 120 degree also there will be least stable structure. But dihedral angle of least stable structure, if we consider, though 120 degree is also present, but better we start from 0 degree. So that is why we will consider it 0 degree, because you cannot say that this is 120 degree. I am saying it is 120 degree because compared to this situation it is 120 degree. But as if you consider this structure when there is no other structure, obviously we will call it 0 degree, right? So that is why last option will be the correct option. Paper chromatography is an example of. Here we have options: partition, thin layer, column, adsorption. First of all, we have to understand that when we are talking about chromatography, the first categorization classification that you can do, partition and absorption, that you have in option 1 and 2, option 1 and 4. Now under absorption, there is both column as well as thin. So this is coming under the heading of absorption. Okay, and under the heading of partition there is coming paper chromatography. So these two are coming under the heading of these two, under the heading of adsorption and partition. Under partition we have paper chromatography. Now what is the difference between these two? In partition chromatography, the mobile phase and the stationary phase both are liquids, but that is not the case in case of adsorption. Here mobile phase is liquid, stationary phase is not liquid. But in paper chromatography both are liquid. Though at a first glance it seems that paper chromatography, on the paper we are giving the spot. So this is the paper. So the stationary phase must be the paper itself. But that is not the case. Here there is some already water molecules present in this paper which is acting as the mobile phase. So paper chromatography is an example of partition chromatography. It is just a type. There are more times possible. And the stationary phase here is basically water, which is already absorbed. When you are using the paper, suppose you have bought the paper, there is already water molecules absorbed in it or trapped in it. Okay. The mobile phase is usually a solvent in which we dip. So here we have given the spot. Now when there is increase in time, gradually all there will be separation. So at a first glance it seems it is single compound, but actually it is now separated to several components. And the solvent front is somewhere here. The solvent flow is here. This is the solvent where we have dipped the paper with the help of this clip. Okay, so correct option will be partition chromatography. Fine. A tertiary butyl carbocation is more stable than secondary butyl carbocation because of which of these reasons? So first thing you have to draw it, right? Tertiary butyl. Butyl means total 4 carbon, but tertiary, that means 3 alkyl group substitution must be present. Now 3 alkyl substitution present to a single carbon, already 4 carbons are there. So that is actually the tertiary butyl. Secondary butyl, here also total carbon is 4, but it is not tertiary. Here it is secondary. Now the branching will be different. So this is the difference. This is tertiary butyl where 3 methyl groups attach to same carbon, and here total number of hyperconjugable hydrogens, that is the alpha hydrogens, 3 here, 3 here, 3 here. So total 9. And in case of secondary butyl means how you will understand it? The carbocation, with this carbon you have 2 alkyl groups both sides. So that is what is secondary carbon, secondary carbocation, and total number of carbon is 4. Now this position is alpha, this position is alpha. So you have total 3 plus 2, 5 alpha hydrogen. When the number of alpha hydrogen is high, obviously the stability will be high. Now it is true that here plus I effect is possible from 3 sides. Here it is possible from 2 sides. So you can say inductive effect is also responsible. But here plus I effect, that is not present in the options. Minus I effect mentioned. But how minus I effect? That is not possible. Plus or minus are these two obviously not possible because there is no resonance happening here. So only option left is hyperconjugation. So that is why we will choose option 1 as the correct option. And because of higher number of hyperconjugable hydrogens in the first carbocation, this is more stable. This is the reason why it is more stable. The compound that is most difficult to protonate. Here, oxygen with 2 atoms or 2 groups both sides, that is common, right? Now, when you are protonating it, it will be positively charged like this. Now, we have to find in which case it will be most difficult to protonate. Okay. Now, most difficult to protonate means the lone pair on oxygen. If the lone pair availability is very less, obviously this lone pair cannot be donated to H+. So basically you have to find in which case lone pair availability less. Now here we have some methyl group or hydrogen in the first 3 options. But in the last option, you have phenyl ring. And when you have phenyl ring and OH, this lone pair will be engaged in resonance with the double bonds of benzene ring. And as a result, you will be getting structure like this. So now see the lone pair, it is already involved. So how it will be donated to some proton? So in this case, it will be very difficult to protonate because the lone pair, it is already engaged. And that is why this will be the correct option. Okay. The number of sigma bonds and pi bonds present in this molecule. So we will draw this molecule first. Paint. That means total 5 carbon. 1, 2, 3, 4. And at 4 position there is ion. So number 5 position you will have this type of that is carbon and then hydrogen. 2 position there will be CC double bond. So here number of pi bonds which is easier to calculate, that we will find. So here we have 2 pi bonds, 1 pi bond, that means total 3 pi bonds, and 3 pi bonds you have only in these options, isn't it? So it is enough to choose the correct option. This will be the correct. But why sigma 10? Because see, 1, 2, 3, 4, 5. This is the 5. Already you can see the sigma. But there is 3 more sigma bonds here. So these 5 also you have to count. So total 5 plus 5, ultimately it will be 10. and that is why total 10 sigma bonds, and the first option is the correct option. Okay, so we'll end the session here. Thank you for listening.